Okay. Today is April the 1st, 2020. And welcome to IME 470. And in the beginning, again, let me stop the video here and share the screen with you. Let's see, screen here. Hello, can you hear me?
Yeah.
Okay, very good. So let me stop myself. Okay. Okay, today we're gonna start lecture 9, okay? So from lecture 1 to 7 are something about linear programs, and lecture 8 is about, the trick of integer programming involving this kind of binary or integer variables to enable model this kind of logic, model this kind of practical problems that it can include logics. And from lecture 9, we're gonna handle some problems like network optimization. This is also the last part of this course. So lecture 9 is something about introduction to dynamic programming. You can download the lecture 9 from the campus connection. A very, very quick review about lecture 8 is here. Let me here. So we introduced the following types of modeling tricks: either A or B, choose K out of N, which is a generalization of either either A or B, which is equivalent to choosing one out of two, and a function with n possible values, dependent variables, and also linearization of absolute functions, linearization of nonlinear functions with finite valued integer variables. I will give you a new homework about this lecture 8, in the end of this week. And today, let's start lecture 9. And oops, okay. And in the very beginning, let's play a game. And again, I would invite people play it with me. So the game description is like this. From 0, I need to have 2 players. I will be one of the player. And one player must add the counting number by either 1 or 2 each time. So you cannot count 0, nor can you count 3. And the 2 players, will add in turn. The one who counts to 20 is the winner. For example, here, player 1 can add 1, so gets 1. Player 2 adds 2, gets 3. And then player 1 adds 1, gets 4, adds 1, gets 5, 7, 9, 11, 12, 14, 16. And finally, player adds 2, got 18, and the player 2 adds 2, gets 20. And so that player 2 wins. Whoever gets to 20 is the winner. Any volunteer want to play with me?
I know how this game works, so I won't volunteer.
Who are you? Sorry, I cannot see you. Let me see.
This is Patrick. I've seen this game before, so.
You're in this game before?
Yep.
Okay, so you know the rule. I mean, you know the trick, right?
Yep. So.
Okay. Okay. Very good. Yes, there's actually a trick, and that is exactly what I want to say. Talk about. Can I take this one there? Okay, a second. Any volunteers other than Patrick? No volunteer? You don't want to add some points? I mean, bonus points to this class? And again, these points will be the points, in your cumulative credits, okay? Remember I said additional 10 points. Due to the coronavirus, we cannot show it on the whiteboard. But still, if you take part in the class here, you can directly, do it here. And I can still add the points to you. Really? No volunteer? Oops, it's here, sorry. No one ever, wants to try the game here? Hey, come on, guys. I know the coronavirus may make it a bit, more difficult to in terms of study something. But I believe you guys will, adapt to it. And after several months, the normal life will still go back. That's it. It's, now it's just a very temporary time. I would strongly recommend you, keep your life routine and be passionate about the life. And that's going to greatly benefit you when this crisis, pass away. No volunteer? Okay. Then I'm gonna directly introduce this game. So here we can see, for example, suppose player 2 gets 16. Then what is player 1's strategy? Player 1 has two choices, either to add it to 17 or to add it to 18, right? However, if player 1 adds it to 18, then player 2 directly gets 20 and it becomes the winner. So for player 1, the strategy will be count to 17. Because once player 1 gets 17, then player 2 will lose for sure. Why? Because no matter you add 1 or 2, for example, you get 18 or 19, player 1 can always get 20. See it? In other words, this game becomes what? This game becomes counts to 17. Whoever gets 17, whoever wins. Now the question is how to get to 17. Similar, if I want to get to 17, as long as I get to 14, I win. Because once I get to 14, the other player can either go to 15 or 16. In no matter which case, I can count to 17, so I win. Again, how to count to 14? You need to get to 11. How to get to 11? You need to get to 8. You know what I mean? And finally, it's actually, what is this operation? It is something like 20 modulo 3 equals to 2. What that means that as long as you get to 2, you get to 5, then you get to 8, then you get to 11, then get to 14, 17, and then finally 20. See it? So be careful about this idea. This idea is very, very important. And this is exactly the DP, dynamic programming, that we're going to introduce in this class. My original target is to count to 20, right? And then I go backward. So from 20, I shift to 17. 17, I shift to 14. And I continue until I shift to 2. In other words, whoever counts first will be the winner, because the first one will count to 2. That's it. And after to justify 8, 11, this kind of very simple tricks, right? So this is dynamic. Why? Because my objective in each stage is changing. In the very first stage, original stage, it was 20. Then it was 17, and then it was 14, and until it was 2. And then I can solve the problem not backward, but just from the beginning, 2 to 5. Okay. And then let me ask you, what if we count to 30, and each time we can add 1 or 2 or 3? If that is the case, how to handle it? Any ideas? Hello, can you hear me?
Oh. Can you repeat the question?
Yes, the question is here. Let me put my spotlight here. What if we count to 30, and each time one can add 1 or 2 or 3? Then how to do it?
Get to 26 first.
Mm-hmm. And then? How to get to 26?
Get to 22.
Very good. And now I guess you know the trick how to make it. By the way, who's talking?
Nathan.
Oh, okay. Hello. So I wish I can have a wide screen, because once I share my screen, in my screen, I cannot see, the kind of like a speaker's view. I know for you have a speaker's view. One side is my screen share, and in your right side is the speaker's view. But in my side, I cannot. I don't know where to find my speaker's view. Once you share the screen, that's the problem. So I cannot see you very. Let me see. However, I can do like this participant. Still, I cannot see. You guys, what I can see is just a list. So, okay, Nathan, you are absolutely correct. In order to get 30, I need to get 26 first, and then 22. And actually, which number you really need to get? how would you estimate it? It is actually 30, and then use the module operation, right? But module of what? 4, right? Then you're gonna get what? You're gonna get a 2, because 4 times 7 is 28 plus 2 equal to 30. So the result is 2 again. In other words, as long as you count to 2 first, then you win. In other words, as long as you count first, you win. See it? Because I can count, 1 or 2 or 3. So as long as I count first, I win. Now let me ask you this question. What if I want to count to n, and each time I can add up to k, from 1 to k, you cannot add 0. Or both of these n and k are positive integers. Of course, n is greater than k, greater than or equal to k. In this case, what is the solution? Hello, any idea?
Wouldn't the solution just be n minus k minus 1?
Yes. N minus, but the question is how to get to n minus k minus 1, right? Because for example, n is 1000, k is 5. So n minus k minus 1 equal to 994. So I mean, but how to get to 994? You know what I mean? In order to do this, you're gonna use this number to minus n minus k minus to minus k minus 1 again, right? And then you're gonna continue until you cannot do it, right? And then what is this? Isn't it a modular operations? You know what I mean? So for example, let's have a look at here. In order to get 30, I need to get what? I need to get 26. Then I need to get 22. Then I need to get 18, right? And then 18 minus 4 is 14, 10, oops. No, 10, and then 6 and 2. From 2, I cannot do it anymore. So this is equivalent to what? This is equivalent to 30 mod 3 plus 1. This is equal to 4. Have you learned this operation? I actually don't know how to read this. Modulo, is it English? Sounds like French. Operation. Do you know this one? This means what? The remainder. So if you use 30 divided by 4, you get what? You get 4 times 7 plus 2 equals to 30. So the remainder is 2. That's how you calculate this. So very similarly, if I have n versus k, the same. So in the first, I want to get n minus k minus 1, right? And then I'm gonna get what? I'm gonna get n minus 2 times k minus 1. Third time, I'm gonna do n minus 3 times k minus 1. And then I'm gonna continue until to a point that I cannot do it anymore. Until, let me say, until r. And in this case, the r equals to what? Or let's say, how do you get to this r? This means n equals to, let's say, x times k minus 1 plus r, right? And r must be between 0 and k minus 2, right? So sorry guys, I made a mistake. Here should be k plus 1 because I added a parenthesis here. So I need to make this plus 1. You know what I mean? So for example, you can consider n equals to 30 and k equals to 3. Then your x equals to what? Your x equals to 7. 7 times 4 equals 28 plus 2 equals to 30. And hence your r becomes 2. Why? Because r has a range that must be greater than or equal to 0 or less than or equal to k plus 1, right? Okay, now the trick is what? The trick is that if this r number is any number between 1 to k, then the one who counts first will be the winner because I can immediately get this r. However, if k is 0 or sorry, here we go. However, if k is 0, then what's gonna happen? Then the second player will win. See it? Why? Because I mean, let's say, suppose I'm gonna count to 28 each time. I can add 1 or 2 or 4 or 3. Then what you're gonna get? You're gonna have a problem because the one who gets to 24 will be the winner, and 20. And if you do it, then it's gonna be 4. That means as long as you count at the beginning and you count first, you're gonna lose because no matter what number you count, I can get 4. Right? Okay. So this is the trick. The trick itself is not a big deal. The big deal is this methodology, the way of thinking. That in order to, for example, go back to the count 20 game, in order to get 20, I want to get 17. In order to get 17, I want to get what? I want to get 14. So when you're thinking about it, you're going to go backward. However, when you're really doing the operations, you're going to go forward. That you're going to count from 2 to 5 to 8. Okay, so this is exactly the idea of dynamic programming, DP. Okay, any questions about this one? Especially, in terms of the methodology. No? I see totally 16, including myself, 16 people. In other words, there are 15 students. I hope you are really, studying, okay? Because here I don't really count your attendance. It's kind of like meaningless if you are here, but you don't, take part in the class. I hope you guys can really enjoy the class. I will try my best to make it, kind of with more activity, and so that you guys can participate more in it. No questions? Okay, let's have a look at the second game. Probably have seen the second game in your SAT class, SAT exams or something similar. So the problem is that here I'm at this point 0, 0. Let me make it maximize. Oh, here we go. Here I'm at 0, 0, and I want to reach to this point 2, 4. And each time I can either go this way or this way. I cannot, go leftward or downward. I can either go upward or rightward. Okay. Then question, how many total ways do I have to reach to 2, 4? What I mean is this. For example, suppose, let me draw a line. Let me draw this. One route is clearly from here to here and then from to here. This is way number 1, right? Okay. And my, where is this? Let me take the bar here. And my way number 2 is, for example, I can go here and then go here. This is the second method. I can go from 0, 0 to 0, 4 to 2, 4. And number 3 is I want to play something interesting. This is the third way I can go, right? And I have too many ways. For example, the fourth way, I can go like this way, right? And the fifth way, for example, I can go like this. For example, I can turn here in the second one rather than the first one. The first corner, I can go this. Okay, so question, totally how many do you have? Anybody gets an idea or no, directly knows the answer? No? By the way, if you want to talk, you need to unmute yourself. Otherwise, I cannot hear you.
Is it around 12?
Around what?
12?
12? Let me see. Nope. A bit more. A bit more. You are close. First, you've learned combinatorics before, right? No, I remember you told me before that for many of you, the first time that you saw the combinatorics is in IME 460, right? If that is the case, then the second method may be difficult for you because in real applications, we're going to solve this one directly by a combinatorics tool, which is super simple, just one step, you immediately get the answer. And that's also the method how I calculate. But this is not the point. The point is this DP idea. Okay, let me show the DP idea. This problem is more difficult than the first problem. Let me show the DP idea. So have a look at it here. Let me circle it. Okay. Suppose I need to go to 2, 4, right? Then let me ask you, This point is what? This point is 1, 4. This point is what? This point is 2, 3, right? Okay. Now I define nxy, for example, n 1, 4 and n 2, 3 to be the number of total routes that I can go from 0, 0 to this point. What is the relationship between n 2, 4 and n 1, 4 and n 2, 3? Let me see, when I can already draw something here. Let me still use a word. Okay, let me see. Okay. Oh, no. So have a look at here. What I want to let me put. Come on, it always go automatically. Here's P4. So what I want to know is what? What I want to know is actually N24, right? N24 indicates the number of routes that I can go from 0, 0 to 24. That's my question. How many routes totally do I have from 0, 0 to 24? Okay. Now the question is, what if I have known, let's say, N1 to 3, 1, 4, and N2, 3. So which means this point and this point. Very clear. How would you get to N2, get to the point 2, 4? You have only two possibilities to go to 2, 4. The first way is I can go through where? Through 1, 4, right? From 1, 4, I can go to 2, 4. This is the first case. And the second case is similar. I can go from 2, 3. Then I can go to 2, 4 via 2, 3, right? So immediately I get actually a relationship. What is that? That is simply N24 equals to N14 plus N23, right? Get a point here? Because why? Again, because how would you go to 24? You have only two ways, either go from here or go from here. So just sum these two numbers, and then immediately you're gonna get N24, right? Then the question is, okay, that means as long as I know N14 and N23, I know N24. Okay, then let me ask you how to calculate N14, for example. Then how do you calculate N14? In other words, I'm asking here. So it actually is the same. Why? Because in order to get to this point, how to reach this point? I have only two ways to reach this point, either from N04 or from N13, right? From N04, I can go from N04, I can go this way. From N13, I can go this way. Either these two ways can give me N14, right? So that similar, I have what? I have similar, I have, let me put it here, copy and paste. I have N14 equal to N04 plus N13, right? And very similar, how would you get, for example, N23? Same, N23 equals to what? Equal to N13 plus N22. And you can do the same. And until what? Until you get to the point of calculating N01 and N10. But clearly, everyone knows what is the number of N01 and N10. How many ways can you go from 0, 0 to 1, 0? Equal to what? Equal to 1. You have only one method. Means directly go from here to here, and you get N01. Or go from here to here, and then you get to N10, right? So in this case, I'm gonna do what? Again, the same idea, okay? I think backward, that is in order to get this point, the total route that I have to go to this point equals to the total route that I have to go to this point plus the total route that I have to go to this point. And then in order to get this point, I need to calculate this and this. To get this one, I need to calculate this. To get this one, I need to calculate this, right? And similar. However, when you're really operating it, you're gonna go forward. That is, you start from n0, 0, then you know n0, 1 equal to 1, and 1, 0 equal to 1, and then this point equal to what? This point equal to 2, right? And then because this equal to 1, this equal to 2, give me 1 second, you need one more thing, which is here. Actually, any points 0, 1, 0, 2, 0, 3, 0, 4, all of them must be 1. And 1, 0, and 2, 0, these 2 points must be 1 as well, right? So in this case, what you have, you're gonna have this one equal to 1 plus 1 equal to 2 is here. And this point equal to 2 plus 1 equals to 3. 3 plus 1 equals to 4, 4 plus 1 equals to 5 here. And do the similar thing, you're gonna finally have what? This number. You know what I mean? So in this case, you just need to use this recursive formula and you can get everything. Okay, of course, if you have a good math background, you can write an explicit formula of this, which is you can use, let's say, the method of induction. I don't think this is very difficult, but anyway, I mean, depends on the math background. If you are interested, think about it, how to directly get a recursive formula from here, from this equation, okay? There's also a combinatorial way, which is super simple, actually. For this, but that way only works for this specific method, okay? It's a special trick. Let me put it here. The combinatorial method. For the combinatorial method here, the answer is directly this. Let me first show you the answer and then tell you why this one is correct. This simply equals, let's say, what is my number here? 4, 2, right? 4, 2. So this simply equals to 4 plus 2, and choose 2. Where am I? I'm here. And this equals to what? This equal to 6, choose 2, which is 15. So that I have 15 possibilities. Why this one is correct? Think about this. What is the total length from from 0, 0 to 2, 4? It doesn't matter which way you go. Your total length must be 6. What that means, for example, consider here, 2 units. And from here to here, 4 units. See it? So your total length is 6. Or for example, you say, hey, I don't like this route. I like another route. Okay, good. 1, for example, here, 2, 3, 4, 5, 6. Again, your total number of length is 6, right? So actually, no matter which way you go, your total number of the length will be 6. Then the question is, among these 6, how would you distribute the horizontal way and the vertical way? See it? What actually you're doing here is you're making a choice in each of the lengths which way you will go, either upward or rightward. So totally how many choices do you have? Totally how would you choose? That is, in totally 6 of the length, I need to choose 2 of them to be horizontal, and the other 4 of them will be the vertical way. You know what I mean? So for example, suppose I choose the first 2 lengths to be horizontal, then I will have this route, which is the first 2 is horizontal, and then the last 4 is vertical. Or if you choose, for example, the first one and the third one is horizontal, then you're gonna have this. The first one horizontal, the second one vertical, the third one horizontal, and all others are vertical. So this means it's a 1-to-1 mapping. Any number, of the 6 total lengths, any of the 2, you're gonna choose them as what? Horizontal way. And the other 4 are gonna be vertical way, upward. So if that is the case, totally how many choices do you have? The choice is 6, choose 2, equals to 15. Okay, so this is a very simple combinatorial method. So what if my destination is X, Y? How many total way do you have? You can definitely use this formula to do the work. However, this is not as fast as this method. Again, for this specific problem. So if I have x and y in this case, what should be the correct answer? So simply you have this. X plus y, choose x. And x plus y choose x equal to x plus y choose y. Okay, this is the basic properties of combinatorics. And this actually equal to what? This actually equal to let's say this actually equals to x plus y factorial divided by y factorial and x factorial. So this is the total number. Okay, so and if you try to get a recursive formula, an explicit recursive formula here, the series here, the consequence actually, what is the number of the series, I think, and then you are gonna get the same answer. But this is not that easy, to be honest. Any questions here? Mainly, we want to show this idea because this topic, this lecture is about dynamic programming. And if you compare this game with the first game, they are the same. The idea, I mean, is the same. Why? Because in both games, I analyze backward. If I want to go to this number, I need to know this two number. If I want to know this number, I need to know this two. If I want to know this number, I need to know this two. And I go backward until the very beginning, or the very initial stage that I exactly know the answer. Then when I'm operating, I'm gonna go upward. I'm gonna go forward, from the forward rather than from the backward. So this is exactly the DP idea. Okay, in general, let's have a look. What is the, let's say, features of dynamic programming? Let's first have a look at a summary. First of all, both of these problems are stage-based. For example, here, stage 1, stage 2, stage 4, stage 5. And here, you know, each point you can consider them consider it as a stage. And the second thing is that to get to the solution to the final stage, we must get the solution to the adjacent or previous stage. In order to get this one and to get this and this, in order to get this one and you get this and this. And for the first game, similar, in order to get 20 and you get 17, and then to get 14, then to get 11, right? So they have these two features. They are also the characteristics of dynamic programming. First, a problem can be divided into stages. Second, the solution to the next stage only depends on the solution to the current stage. This is called the principle of optimality of DP. DP is dynamic programming. And we need to get a recursive formula or a recursive relationship. And yes, we can do it. Why? Because of this principle that the solution to the next stage only depends on the solution to the current stage. In other words, suppose I know, let's say this, suppose I want to know the weather of tomorrow. I only need to know the weather of today. That's it. I don't really need the weather of the day before yesterday. What I mean is direct relationship, okay? Direct relationship. By the way, have you learned Markov chain or Markov property in probability? I don't know whether if, let's say in what's the course, 461, did the instructor introduce the Markov property? No? Or yes? Can anybody give me an answer?
No.
No? Okay. So the Markov property is something very similar, that in order to know the status of time t, this is something about time series, a little bit deeper than the probability theory. In order to get xt, I only need to know xt minus 1. Xt, oops, actually I want to say this, is known, let's say xt is only directly xt only depends on xt minus 1, where this x is a random thing, a random process that you don't know. And I have t. T means time. And this is widely used in many stochastic, analysis or time series. For example, xt can indicate the number, the price of stock, of one stock at the time t. And xt minus 1 means, for example, the stock price yesterday and what's going to happen. Or x can also indicate, for example, the number of coronavirus cases of, let's say, today. And then I want to know how about xt plus 1. In other words, tomorrow, how many cases totally there will be. And I don't know the distribution. That's the problem. If I know the distribution, everybody can calculate it. The question is I don't know. And the distribution can be with a parameter of t. And that is also some difficult problems for CDC. And you may be interested, hey, so how can they predict that the darkest time would be in about 2 to 3 weeks? That is the rush about the death or the cases. How did they know it? I plan to make a video. I will upload to my channel as well, something about a logic model. And if possible, later I may make an SRGL SRGL model as well, about how this kind of diseases will be spread. If you're interested, you can check the channel and I will post it, okay? But that is something not really related with this probability analysis. That's something about using the ODE, ordinary differential equations to calculate it. So the point here is that this property is the same in Markov chain, or the same as Markov property. The difference that here we're talking about something deterministic, but in Markov things, usually we're talking about something stochastic, or a distribution with time, with a time, t, with a domain, so that they're somewhat different. Okay, there are two very famous problems about dynamic programming. I would say they may be two the most famous problems in terms of DP. One is the shortest path problem, and the other is the knapsack problem. Here, I'm going to introduce the unbounded knapsack problem. And let's see what they are. For the shortest problem, it's pretty simple and direct. That I want to find the shortest path. Path means a directed graph, okay? I can go from A to B, but it's hard to say that I can go from B to A as well. For example, consider the University Boulevard. It's, around the campus, it's a one way. You can only go which direction? Go south. You cannot go north. Otherwise, you're gonna get a ticket very easy. Now, I want to ask, what is the shortest path, for example, from the university to Walmart? And I want to, get it. Everybody probably will at that time, take out your cell phone and then go to Google Map, or maybe directly the Apple Map, which is basically on the Yahoo Map, and then say, hey, tell me, iPhone, what is the shortest path, right? But what is the principle? Have you thought about it? How did the cell phone, or let's say, how did the app calculate it? Here you go, the shortest path. And here, what do we say path? It doesn't have to be a physical path. It can be, for example, really a distance, which is a physical path, or time, or profit. And then I think in the next lecture, lecture 10, I'm going to show you how to model kind of like a decision making to maximize to minimize your loss or maximize your profit. It's something also shortest path problem. And in terms of time, it's even more applied. For example, in most of our smartphone, on default, it's set as the shortest time rather than shortest route. For example, in this figure, I actually got it from my cell phone, and you can see, for example, this one is 15 minutes. Yeah, so why it chooses this one? This is 15 minutes, and this is 30 minutes. And this one is 5.3 miles. This is also 5.3 miles. Then question, why did the app choose this one? I don't, okay. Because at that time I set it as there's no highway. Yes, here you go. You have a highway here. This small part, 66, see? This is I-29, right? I-29, I think. I-29 or I-94. This is I-94, so this is I-29. So it avoids the highway so that it gives you this way, okay? And usually it is the shortest time rather than shortest path. And that's also the reason why usually if you input a destination there, it's gonna show several ways. One of them usually is shortest distance, and several others may be some other options like shortest time, or for example, no highway option, something like this. And the shortest path problem is also widely used in this kind of decision making. And we're gonna see in the next lecture, okay? So in this lecture, I'm gonna introduce the very basic thing, which is if I have a graph and I give you S and T. So I want to go from S to T, and I'm asking what is the shortest path from S to T. Here, all this kind of weights means distance. In real applications, for example, it may mean cost, or it may mean distance or time, whatever. You know, they're the same. Topologically, they're the same. So, for example, I have this graph. I'm asking how to go to go from S to T, so that my total length, my total distance will be minimized. This is the shortest path problem. And so we're going to introduce a DP algorithm called the Dijkstra's algorithm. How many of you have learned this algorithm before in a computer science class? This is too famous. I guess many of you may have already known it in high school or in some computer science in let's say the first year or the second year of the college. How many of you have heard of it already? No? I don't know whether you haven't heard or maybe you didn't pay attention to my question, maybe? I mean, the Dijkstra's algorithm? No, nobody
I haven't heard of it.
Oh.
Heard of it? The name, I mean, no? Okay, anyway,
Never.
there are many different versions of the Dijkstra's algorithm. Today, I'm gonna introduce you a version about DP, and I believe this is one of the fastest DP, I mean, in terms of the Dijkstra's algorithm. Let's have a look at it. So, come on. Okay, let me directly use the keyboard. Use the mouse, it always automatically, go up and down. Okay, so first of all, I want to introduce some very, very basic notations and ideas. First of all, let's go to the characteristics here. First, a problem can be divided into stages. Second, the solution to the next stage only depends on the solution to the current stage, and hence we can get a recursive formula. Let's see whether it's correct in terms of the shortest path. Okay, now I want to get a T, right? Okay, and I'm asking what is the shortest path to go to T. Okay, now let me ask you, again, suppose I use Fi to denote the shortest distance from node S to node I. For example, Ft as the question that I'm asking. If I know Ft, I'm done, right? The question is, if I want to go to T, how can I reach T? I can only reach T from one of the following nodes. They are node 2, node 3, node 4, or node 6, right? So finally, if I want to go to T, it must be from one of them. But I don't know, of course, which one. Okay, now let's use this notation. If I have already known the shortest path from S, I mean the shortest distance from S to 2, and the shortest distance from S to 3, to 4, to 6. Can you tell me what is the shortest distance from S to T? Similar, I'm gonna use this formula. Remember, this formula is very similar to this formula. The difference is that here it's deterministic. Why? Because the distance is fixed to be 1. However, here it is not. Why? Because, for example, from 2 to T, the distance is 19. 3 to T, it's 6. 4 to T, 16. 6 to T, 44, right? So what you need to do is to get a minimum. What I mean is this. Suppose you have already known the shortest distance from S to 2. So what is the distance, shortest distance, if you go, for example, from 2 to T? And I force you to go from 2 to T. You have no other choice. I mean, 2 is the last node, okay? You cannot say from about 2 to 4 to T. No, it's not. Actually, you can see 2 to 4 to T is actually closer. 2 to 4 to T costs you only 18, see it? 2 to T directly is 19. But here I force you. You must go from 2 to T. So you have no choice but cost F2 plus 19, right? F2 is the shortest distance from S to 2. And this 19 is from 2 to T. Your cost is 19, okay? So this is the case if I go from 2 to T, finally. And this is the case if I go from 3 to T. F3 is the shortest distance from S to 3. And this 6 means from node 3 to T, the cost. And similar from node 4 from node 6. So total, I only have these 4 cases. And if I want to minimize them, suppose I've already know F2, F3, F4, and F6, then for sure I know Ft. Right? Clear? This is very important. Please spend some time to understand this. Okay? Clear? Okay, now continue. In other words, if I know F2, F3, F4, and F6, then I know Ft. Great. Question is, how would you know F2, F3, F4, and F6? For example, how would you calculate F2? Very similar. How can I go to F2? How can I go to node 2? I have only totally 3 cases. I can go from 1 to 2, or 5 to 2, or 3 to 2. Must be one of them, for sure. Again, very similar. If I have already known F1, if I've already known F5, if I've already known F3, what I need to do is this. I only need to calculate this one, right? Using exactly the same idea as this. They're the same. See it? The minimize of F1 plus from 1 to 2. The minimize distance of F5, and then from 5 to 2, which is 18. Then the minimize of distance from S to 3, then from 3 to 2. That's it. So use this formula, I get F2. Again, how would you get F1, F5, and F3? For example, F1 can only go from S to 1. So that for sure I know F1 equals to 9. See it? How about F5? F5 can only, F5 similar, F1 S to 5. So I know F5 is 11. How about F3? Well, F3 is a bit more difficult because I need to know F4. How to know F4? I need to know F6 and F5. How to know F5? Derivative S. How to know F6? Either derivative from S or from 5 to 6. You see it? And hence we get a very important, which is the most important, I think, and the recursive formula here. Extremely important. That is, if I want to know the shortest distance from S to node J, then that equals to from S to I to node I, the shortest distance from S to node I, where I is a point from which I can go to J. For example, suppose our J equals to 4. Then the candidates of I are 2 and 5 and 6. Why? Because from 2 and 5 and 6, I can go to 4. Plus the weight from I to J, which means plus the weight, for example, from 2 to 4, or plus the weight from 5 to 4, or plus the weight from 6 to 4. Okay, and here A is the arc stat. Ij is in A means there exists an arc from node I to node J. For example, S1 is in A. Why? Because yes, there's an arc. See, from S to 1 from the graph, I have this arc. A2, 1, 2 is also in A. Why? Because 1, 2, there's an arc here from 1 to 2. See it? Let me make it bigger. From 1 to 2. See it? But 1, 5 is not in A. Why? Because from this graph, I cannot go directly from 1 to 5. See? Be careful. I'm talking about directly. Okay. For example, 5, 3 is also not in A, because there's no direct arc from 5 to 3. Although I can go from 5 to 4, 4 to 3. No, it doesn't count, because this means a direct, link, or a direct path from I to J. Okay, so in this case, my A, this gets my arc set A. I think where I have a, okay, here we go. Here we go. I have a clear definition of, let me see how to, oh, okay, here's the pen. So in this graph, A is this. Sorry, I try to make my mouse well. Okay, so here I totally have how many? 1, 2, 3, 4, 5, 6. I missed a comma here. 7, 8, 9, 10. 1, 2, 3, 4, 5. Total I have 15 arcs, and I think you can really count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. See it? So in other words, what is A? A is any arc that there's a direct link. For example, 5, 4 is there, 5, 4. 2, 4 is there. Where's 2, 4? 2, 4 there. But you don't have 4 to 2. Why? Because this is a one way. You can only go from 2 to 4, but you cannot go from 4 to 2. Okay. So this is the arc set. Okay. Okay. Due to the time limit, I'm gonna stop the class here, and I have a homework, a very temporary homework for you guys today. Right after today's class, please review these 8 slides. what I mean, especially from here, from page 5 to page 8. It's very, very important for you to, get the point, especially a rough kind of like the idea, what is the DP and how to apply this recursive formula in the DP. And finally, we're going to introduce the Dijkstra's algorithm in details, and you can see we'll have a lot of iterations. And you can see every time what we are doing is to repeat this formula and then fix a node, repeat it, fix a node. Actually, we're doing just two things, and we're repeating. However, you do need to understand this formula first rather than mechanically apply it. Otherwise, it's going to be really meaningless, and very painful. Okay, let me see. Here's everything about today's lecture. Thank you very much. Again, a reminder, you will have a homework due on Friday. Please don't forget to submit it on time. That's everything. Thank you very guys. Have a good day. Bye-bye.